Computer science is more than just about coding, compiling, and finding irritating bugs in your codes somewhere at line 12. At its core, computer science is about problem solving, and a good way to know how it does this is by learning automata theory. But first, what are automata? Automata, meaning abstract computing devices, are mathematical models used to solve problems. An input goes in the machine, and a resulting output appears. By using these mathematical models, we can assure that anything that is solved in these machines can be solved at any real-life computers, may it be Windows, iOS, or Linux, and in whatever programming languages it may be written on. The finite automata is one such model, which is a very simple computing model which acts as a language acceptor, meaning it takes an input string and outputs either yes or no based whether or not the string is part of the language. However, this is not a general model of computation, and it only works for regular languages. Finite state machines have three parts, namely the states, the start and accepting, transitions, the state and input, and control, which transitions the state to state in response to inputs. It only remembers what state the control currently is, making it a good model for an extremely limited amount of memory. There are two types of finite automata, which are the deterministic finite automata, or the DFA, and the non-deterministic finite automata, or the NFA. The deterministic finite automata is when given an input, the finite state machine transitions exactly to one state from its current state. For a DFA to accept a string as part of the language, it must read the string from beginning to end, following the transition functions for the input. Once that it reaches the end, it will accept the string if the last state is one of the final states. Otherwise, it is rejected. The non-deterministic finite automata, on the other hand, is when given an input, the finite state machine can transition from one state to multiple states. It accepts a string if any sequence of choices lead to any of the final states. There is also the epsilon NFA, or NFA with epsilon transitions, that allow a state to transition to another state without taking an input symbol. However, despite these capabilities, the epsilon NFA and NFA are not a more powerful model than DFA, since all of them only accept regular languages. In fact, these are convertible to one another. A language that cannot be recognized by finite automata are called context-free languages. Defined by some context-free grammar, or CFG, this is more powerful than finite automata since it can define more languages. This is because regular languages are only a subset of context-free languages, although still, this cannot define all languages. CFGs can also count two things but not three or more. However, there is an automata that can recognize a context-free language, and it is called the push-down automata, or PDA. This is an epsilon NFA with a stack, meaning it allows transition on an empty string input and utilizes a stack, or the last in first out data structure, to allow itself to count two things, which is similar to the CFG. It also has better memory capabilities than finite automata because it can remember the current state and the stack contents. Since both the CFG and PDA can count two things and have the same language defining power, they are equivalent to one another. This means that we can create an equivalent push-down automata given any context-free grammar and vice versa. There is, however, a more powerful model than any of the ones that we have discussed as of yet, and this is called the Turing machine, named after its inventor, the late Alan Turing, wherein he modeled a general-purpose computer with an infinity. Intended as a hypothetical computer and not for practical use, its goal was to understand the limits of computations. Since it is a theoretical machine, it is as powerful as any general-purpose computer in terms of computing power, but it is more powerful than our current computers since it is infinite in memory. These computational models are used today to answer very difficult problems because our computers are, however advanced they are in software and hardware, limited. The computers of our present are called deterministic, meaning they can only transition to one state on a given input. They do not have the power of non-determinism, which always correctly guesses choices that lead to optimal answers. One of the greatest unsolved problems in computer science is the notorious P versus NP problem. P means problems with the polynomial time algorithm, or PTA, run on a deterministic computer, while NP means problems with a polynomial time algorithm run on a non-deterministic computer. It is known that if a problem has a deterministic PTA, it also has a non-deterministic PTA. However, we are not sure if the converse is true. That is, if a problem has a non-deterministic PTA, it is unknown if it also has a deterministic PTA. If it is proven that a problem with a non-deterministic PTA indeed has a deterministic PTA, or P equals NP, then it means that all NP problems also have a deterministic PTA. However, if the contrary was proven true, where P is not equal to NP, then it means that all NP problems will take an exponential time to solve. This uncertainty is literally a million-dollar question, and the implications of which will shake our society. Because if P is not equal to NP was true, then NP problems will have at least exponential running time. However, if P is equal to NP was true, then NP problems can be solved in reasonable time. But this means that our modern cryptography methods will cease to be useful because there is a way to crack this security in a reasonable amount of time.
What the hell we gonna do now?
That is why automata theory is an important topic. Within this study, computer scientists learn more and more about the limitations of computing capabilities. Even without a physical computer, they can answer from the simplest to the very complex computational problems. Problems that have a gigantic effect on our world and our understanding of computing. So what do you think? Isn't it cool how these things work? From finite automata to million-dollar questions you couldn't seem to get an answer of from the previous NP problem, computer science makes this world turn a little bit more interesting, one bit at a time.